Okay, so as a finishing touch for this unit, we can gather everything we have just said about the information that the Taylor polynomial can give us about the behavior of a function, and we can use all this information to actually graph the function, okay, and sketch its behavior, right? And so for that we need to check 7 points, right? The first one is to check what's the domain, okay, of the function first, in order to graph it properly, right? Then the second one, it's useful if we, and helpful if we find symmetries, right? So if the function is even, if it's odd, if it's periodic, right? So it says in the first 2 cases, it's enough to represent the function from positive x, because the negative x's are just the symmetry of that, right? And then if we have a periodic function, we just need to represent the function in one of the periods, in one of the intervals, because then we just need to repeat that graphically. There are other symmetries possible, such like that the function is symmetric around vertical axis that's not 0, for instance, and so on. But in general, it's going to be these ones. Okay. Now we need to check where the function is continuous and differentiable in order to see where the function jumps, and when we have these cusps, these things where the function are not differentiable, right? And also useful for detecting extrema, right? Now next, the zeros, where the function crosses the x-axis, and so says these points separate regions where the sign of f remains constant, obviously. Now then we need to check where the function grows and decreases, and so in other words, to find the solutions of f prime equals 0, so that we can find the extrema and the point where it grows and stops growing. Okay. Next, the convexity of the function, so that we can see the function is concave or convex, right? And that's helpful to plot it. And then from that get also inflection points. Typically we will need the second derivative of f for that, but if the second derivative is 0 at some points, that we, if it's always 0, then we will need higher derivatives, as we have seen in the previous video. And then finally we want the asymptotes, right? So are the curves which f approaches when it gets close to some point, or to plus minus infinity, right? So we need to check the vertical asymptotes. It's usually when the function diverges at some point x equals a, so it's the limit when x go to, so these are the values of x where such that the limit when x goes to a on the right and on the left is different, and so we have either plus it goes to plus infinity on one side and minus infinity on the other, or just plus infinity, something like that. Okay, the function is divergent at that value a. That's a vertical asymptote, right? Horizontal asymptotes are the limits when aligned with the limit when x goes to plus or minus infinity of f. Okay, and you get some value L. Okay, it could be different at plus and minus infinity, for instance. You could have this. Okay, and then you have inclined asymptotes, which is where the function grows to be something like a curve, right? So something like a real line. Okay, so you say that y is equal to mx plus b is an asymptote of f when the limit when x goes to plus minus infinity of f divided by x is a constant m. Okay, so that means that when or if you want divided by mx is 1, right? So if you want the difference is that when x gets very large, this function f is asymptotically equivalent to mx, right? So it's growing like a line, right? Like a straight line. Okay, and in order to see, but you could have mx here, you could have f of x here. You want to shift this line so that you get it close to f, and in order to do that, you have to compute the limit when x goes to plus minus infinity of f minus mx, okay? And the difference between these two lines will give you b, which is the intercept of the asymptote that you want to compute, okay? So what it says here, in other words, it means that f of x is equal to mx plus b plus small o of 1 when x goes to plus or minus infinity, okay? Obviously, we can also get other asymptotes, and in general you will have that g is an asymptote of f if when x is very large, if f is g plus small of 1 when x goes to plus or minus infinity, okay?